Here's chapter 4 of electromagnetic theory. In this chapter, we will cover the wave equation for uniform plane wave. We will discuss the property of plane wave as well as the so-called TEM wave, transverse electromagnetic waves. Wave properties such as the propagation velocity, phase velocity, groove velocity. You will hear different kinds of the names, and you will be able to differentiate what the difference between phase velocity and groove velocity. Other terminologies such as wave impedance, standing wave ratio will be discussed. And next week we'll talk about wave in lossy media and polarization properties of electromagnetic wave. So here is the wave equation. So it starts with the Laplacian minus gamma to the square. 那个不是 r， 那是 gamma. Gamma to the square times phi. That's the form of wave equation in lossy media. And therefore, gamma is a complex number. It has the real part alpha, which is referred as the attenuation constant, and the imaginary part beta, and is referred as the phase constant. So gamma equal to alpha plus j beta is the so-called propagation constant, 传播常数材料的So the real part of the propagation constant represent loss in the medium, okay? And wave equation, the form of wave equation, one critical part of all wave equation is it describes the field difference in space and in time simultaneously. So 波动方程式里头重点在于它的那个电场或磁场，它的时间变动跟空间变动是同时被描述的。所以前面那个拉普拉斯倒三角形记号描述的是空间上的变动，那后面那个伽马平方它其实是时间的二次方其实时间的二次变位分，所以它包含了时间的变动。OK。So for the first sign, the del to the square, the Laplace operator describes the spatial variation of the field. While the second term, gamma to the square, describes which is derived from taking time derivative of the field twice. Okay, so it is the second order differentiation result of in the time domain. So the wave equation comprise spatial variation and the time variation at the same time, simultaneously. All right? And for lossless medium, the gamma is reduced to j beta. So j beta to the square is minus beta square. Okay, so if you substitute gamma to the square with minus beta to the square, you end up with del to the square plus beta to the square times phi equal to 0. So that's your wave equation in lossless medium. And it's still a complex wave function. And next is beta is as I mentioned earlier, beta is referred as the phase constant, 相位常数. And it can be expressed as the product of the omega, the angular frequency, times square root of mu times epsilon. Mu is what? Permeability and permittivity. Mu and epsilon are permeability and permittivity. 介质系数跟介电系数嘛，So therefore, the square root of mu times epsilon is actually what? The inverse of speed of light. speed of light. Okay, speed of wave. Okay, and all right. So in this chapter, the important thing that you should know is the form of solution of the wave equation. Okay, so wave equation phi can be electrical field or magnetic field. So it's a general expression for E and H field. As you can see here, is in the parenthesis of R. So this is not gamma, this is R. This is the description for position 啊，所以位置的描述嘛啊，所以在3D 环境的话就是 X Y Z。Okay, so phi is a function of position. Phi is also a function of time, but you cannot see the time dependence in this formula, right? Time, where's the time? Where's the time? Well, time is actually hidden in the so-called Phasor form. Okay, for graduate students in this class, you are supposed to understand that when it comes to the representation of EM waves, we usually write EMH field in Phasor form. Suppose we know that the field belongs to a sinusoidal signal of a specific frequency 啊，所以假如我们知道这个电磁场或这个电磁波是属于某一个特定频率的波动讯号的话，那我们事实上会用Phasor form来去写，让它的表示是比较干净简单啊，因为你知我知，它都是特定频率的讯号，所以那个 time dependence 我们就有点把它省略了，不写。但是它在那里啊，你要知道它在那里啊。OK 哈， so even though we didn't write the time dependence explicitly in the formula, you should know that it's in there. Okay, so it's in the form of the time dependence is in the form of my exponential j omega t. So it's used to be represents the sinusoidal the time dependence of the wave of a specific frequency. Okay, 所以它是用来表达 cosine omega t 的 ，right? But you cannot put an equal marker between the two. No, you cannot do that because close to what? So they are not the same. But if you're taking only the real part of exponential j omega t, you will end up with cosine omega t. So this is the so-called Phasor form. If you want to express the field in instantaneous form, okay, so this is the instantaneous form. 瞬间的那个场的表示式啊。所以这是最正确的啦，下面这个是最正确的 actual representation 啊，它 instantaneous form. You need to times your Phasor expression with the exponential j omega t term and then taking the real part of it, you will end up with this. So look at the Phasor representation of the field again. You see it can be divided into two parts. The first part is the amplitude term. So the first one is referred as the amplitude function. Okay? And again, the amplitude of the field is also a function of position. Will it be a function of time? Of course. But we didn't write it explicitly, explicitly, 明显的把它表示出来 okay? And the second term of the Phasor representation is the phase function, okay, phase function. So it's written as capital phi of r. Again, this is a function of position, And this is the location vector in Cartesian coordinate system. Okay. Sometimes you can write like this. That's the same thing, all right? In other textbooks, but here it's used just x hat to represent the unit vector of the actual unit of the three principal axes. All right. So once we have the wave wave function representation, we can move forward to introduce some special property about waves. Here we will look at the so-called uniform plane wave. 你知道什么？平面波 ，plane wave 是平面波 ，uniform wave 是什么？一句一致性的平面波嘛，哈。So first thing we like to describe here is the equal phase surface, which of course, as the name suggests, on an equal phase surface, all fields have the same phase. Okay. 郭老师啊，你来我会开始紧张了。OK. 好，没关系。Okay. So for equal phase surface, all points on the surface shall have the same phase now shall have the same phase. Okay. And if the equal phase surface forms a planar surface, of course, it can be referred as the uniform plane wave. And here are some description for the some examples. To the left are some example of the equal phase surface description. Okay, one is a constant, and the second one phi equal to 4x plus 5y plus 6z as a constant. So it's actually a geometric description of a tilted plane. Tilted plane, OK， 所以斜摆的一个平面的话，斜摆的平面的描述。And the third one is phi equal to x to the square plus y to the square plus z to the square. This is the spherical wave. Spherical wave. Okay, so which means that the distance of any observation point to the origin is a constant. It's a constant. So you can, with different constant number, you can get spherical wave spheres of different radius. All right. So waves are uniform when the amplitude function. Okay. Again, the field distribution comprises the amplitude function and the phase function. And all right, so if phi r is a constant, you have equal phase surface. If the amplitude function is a constant too, then you have the uniform wave. You have a uniform wave, okay? You have a uniform wave over the equal phase surface. The vector phase constant beta equals to minus the negative of the gradient of phi. Phi is the phase function. 相位函数phi 是相位函数。相位函数的什么？梯度 ，OK。我们复习一下For spatial differentiation operator, you have curl operator, You have divergence operator. You have gradient operator. Okay. So they are all spatial derivative of vectors. The first two are spatial differential operation on vector. The third one is on scalar. But anyhow, they are examining the field distribution in space, checking out if they are uniform, if they are the same in the space. So what is the difference between Kerr and divergence? Kerr is also referred as the lateral differentiation, okay? Which means if your field is pointing toward this direction, the Kerr operator examines the difference in transverse direction, 侧向的，跟它原来场的方向正交的方向，所以叫做 lateral differentiation， 侧边 lateral 是横向的，侧边的。所以 Kerr operator is examining the fields distribution in space in transverse direction, while the divergence operator is examining the spatial variation along with the vector direction, which is in parallel with the vector, right? So it's referred as the longitudinal. It's the longitudinal derivative. Okay, lateral derivative for Kerr operator, and longitudinal derivative for divergence operator. Gradient is easier to understand. It just examines the difference, difference of the vector of the parameter, the scalar parameter in space. So if it's not homogeneous, you end up with a non-zero gradient. However, by definition, gradient phi is a scalar. What is the result of gradient of phi? Gradient of phi. Is it a scalar or a vector? It becomes a vector. A vector of what? The vector of what? The gradient of phi identifies the direction and the amount as well, the magnitude and the direction as well. The direction of maximum rate of change, 最大变化的方向phi 是一个空间中场的空间分布的存量描述，而梯度 gradient 的操作会给你说 phi 在哪一个方向的变动最剧烈，哪一个方向的变动最大。所以 therefore, if you have equal phase, which means that on this line, the phi, the phase on this line is the same. So, what will be the result of gradient operator for phi? For gradient of phi? If you move along the equal phase direction, there's no difference in the phase, right? If you move along this direction, no phase difference. If you move this direction, some difference. You know, when you move forward, suppose that the wave is moving from the left to the right. So you move along this arrow, this direction, you experience some phase change. But what direction will give you the maximum change of phase? The direction that is perpendicular to the surface, the direction that is orthogonal to the plane. 所以跟那个面等相位面正交的方向可以给你最大的相位变化率。Okay, so that will be the direction of gradient of phi. Okay. However, gradient of phi is finding the direction of the maximum change of phi to a larger number. Okay. But so it turned out moving to this direction, right? So for wave propagation, the actual propagation is beta, okay, beta, and it turns out to be the negative of the gradient of phi, right? And sometimes the phase constant, you know, now it's a phase constant vector, okay? So you notice that the beta becomes a vector. So it not only gives you the magnitude of the phase constant, it also point out the direction of phase change, direction of phase change， 像也就是波行进的方向了哈，所以贝塔其实是已经是变成波行进的方向。In some textbook, beta is written as k, right? So when you come across to beta, okay, just check up. You need to check up the text before and after that to make sure that it's referred to the phase function, the vector phase function. So beta is referred as the vector phase constant, and it is perpendicular to the surface of the equal phase surface, and hence represent the wave propagation direction. Okay, right. So the important thing is here; it represents the wave propagation direction. Right? Any questions so far? 没问题到这边啊。And as we know, by definition, the vector phase constant is the result of the negative of the gradient of phase function phi. So it's a vector. So it has projection on x, y, and z axis. So the three projection of beta, beta x, beta y, and beta z, and they can be found very simply in Cartesian coordinate system, in rectangular coordinate system. They are just the spatial derivative of the phase function phi over x, over y, and over z, all right? And it can be understood that beta x, beta y, and beta z are the projection of the vector phase constant beta on x, y, and z direction. So, what is the relationship between beta and beta x, beta y, and beta z? So if you are taking the square of beta, you agree with that? And also, the beta is a positive number, positive real number. Because beta is a positive real number, so beta is actually greater or at least equal to beta x, beta y, and beta z. Agree? 同意吗？啊，因为贝塔本身是正实数，所以我不需要，我应该不需要绝对值哦。 好了，只要这样写的话，就是不是向量用存量的用 magnitude 的方式来看它哈。所以一个向量在直角不只是直角坐标系统啊，任意坐标系统里头，它的 projection 都会比它小嘛，可以吧？同意吗？好，要讲这个原因是因为等一下后面要埋一个梗啊，等一下后面会用到啊，等一下后面用到。And of course, the propagation direction function, the propagation direction of a uniform plane wave can be any direction. Can be any direction. 可以任意定义。So a plane wave propagates in x direction can be written like this in Phasor form. So the magnitude is u sub 0. U sub 0 is a constant. So the magnitude of the wave is a constant as it propagates along the x direction. I would say it's propagating at the x direction because the phase function is jk minus jk for so the phase function is minus kx. Minus kx. It's only a dependent. The function is only a dependent of x. So it's moving along the x direction, not in the y and z direction. 只有在坐标系统里头，只有对 x 方向有变化。Okay. So here is the definition for the phase function. Then by taking the negative of the gradient of phi, you end up with the vector phase. So here is the vector phase constant. By taking the negative of the gradient of phi, you end up with kx. So it's moving toward the positive x direction or negative x direction. Positive. OK 往正 x 方向传，而它的大小方向是 x 方向是 x 方向，大小嘞 k OK so you can identify k as the phase constant projection of the phase constant function along the x direction. Okay. So to describe a plane wave propagating in the positive x direction, you need to have, that is, the phase function. The phase function equals to minus kx as a constant, right? So if you times the wave representation, the uniform plane wave representation with exponential j omega t. So we put back the time dependence and taking the real part, you end up with the instantaneous form of the wave. The uniform plane wave propagating along the positive x direction. All right. So you have u sub 0 cosine omega t plus phi. Phi of r, actually phi of x, right? So the important thing of propagating wave is that you need to have time description and spatial description in the same time, simultaneously in the cosine function. 这我在大学部的电磁学里头，我在强调的事情，就是对于电磁波来讲，一个会传播的波，一个 traveling wave， 一个行进波，它的重点在于你对于这个波动的描述要同时包含时间以及空间的描述。所以 所以我常常讲的就是它是 cosine omega t minus beta z 嘛，omega 这边的话是 omega t minus kx 所以第一个是时间的描述，第二个是空间的描述 ，right？ Okay. The next thing we'd like to discuss is about the velocity. Velocity. What is velocity? The speed of moving. So when it comes to the velocity of waves, we refer to speed of the moving of the equal phase fund. 等相位面移动的速度 ，OK？ 有没有看过冲浪 ？Have you ever seen surfing? What does it take to be described as I'm surfing? I'm not plunging into the water, right? I'm surfing successfully. Which means you and your surfing board moving at the same speed as the wave. Okay? When you successfully do that, you move at the same speed with the wave. You and your surfing board move at the same speed of the wave. You kind of standing on the wave and look quite marvelously, all right? Looks very good, okay? And you can enjoy this moment for 3 seconds, 10 seconds, depends on your skill. But once your moving speed and the wave propagating speed are not synchronized, well, either the wave is falling apart or you fall below the waves. Well, do that again, right? So we come back to the wave, the velocity of the wave. We mean the phase velocity, all right? So 那个浪头上面其实就相当于你一个正弦波啊，或者是一个等相位的，就是相位移动的速度啊。所以我们这边看到的速度指的是相位移动的速度。所以你在冲浪的时候站在浪头上表示你的速度跟浪的传播速度，或至少那一个方向的向速度是一样的。Okay? So we know that the speed of the wave is the phase velocity, okay? So when you look into the description of the phase function, that means the content, the parameter of the phase function should be a constant. That is, and the phase function is cosine omega t minus kx. And it implies that omega t minus kx should be a constant number, right? 所以它的只要相位是一个定值的话，那就是 omega t minus kx 是一个定值，is a constant. So if omega t minus kx is a constant, you taking derivative on both sides, you end up with omega dt minus k dx equals to 0. You must search this equation a little bit. You end up with dx over dt equals to omega over x. So omega over x is the phase velocity of the wave along the x direction. 沿着 x 方向的向速度，所以也不是很困难了对不对？Omega over k, omega over k. So here we can review the uniform plane wave property. We already talked about this, so let's take a quick look. So here is the field vector in Phasor form. You have the amplitude function, you have the phase function, and the vector phase constant is the negative of the gradient of phase function phi, and here is the phase wave equation in lossless medium. Okay, if you want to have the actual instantaneous description of the wave, you need to time the wave function with exponential j omega t and taking the real part of it. And the important things when it comes to the speed of the wave is that the phase function need to be a constant. That is omega t plus j plus phi of r equals to a constant. And the wave propagation direction beta is not only a description of the phase constant, but also a description of the phase propagation direction. And it's defined as the negative of the gradient of phi. So it is perpendicular. It is perpendicular to the equal phase front. 跟那个面，跟等相位面是波的等相位面是正交的波的等相位面正交。And of course, wave can be propagated in any direction in the space. For this particular case, for the particular case we have just discussed, we choose x, positive x direction as the wave propagation direction. So by definition, the Vx, the velocity, phase velocity in x direction is defined as dx over dt, where dt can be, when it can be substituted with the terms we found in the phase function, omega over minus of spatial derivative of phi with respect to x, and that is omega over beta x. So beta x is what? Beta is the phase constant beta, the projection of phase constant beta along the x direction. Right? So if you do the same thing, we can find out the phase velocity along the y direction. It's defined as the omega over beta y, where beta y is the projection of phase constant beta over the y direction, and so on and so forth. You have the phase velocity of vz along beta z, right? So here is some interesting stuff. But first of all, we should look into the description in the text. If ds change along the surface because gradient of phi equal to 0, by definition, the phase velocity will be infinity. Right? Right. Let's see if I can get this right. So in the previous slide, we have Vx equal to omega over beta x. The phase velocity along the y direction is omega over beta y. And velocity of the phase along the z direction is omega over beta z. And from here, we know that is greater or equal to beta x, beta y, and beta z in general, right? So what is this? Comparing to the statement over here, that should be what? The phase velocity. The phase velocity of the wave along its propagation direction. 好，所以这个是像素度了，这个描述了，因为欧米伽 over 贝塔的话，用角频率除上相位常数的话，它就是像素度啊。从这样定义的话是像素度。那这个像素度就会是你那个波沿着它传播方向的像素度。那你有没有发现一件事情？ The phase velocity of the wave actual propagation in the wave propagation direction is smaller than the phase velocity of the wave projected on x, y, and z. In fact, it's smaller than projection of the wave along any direction. 啊，也就是说，像素度的 在任意方向的投影量都会比它原来的像素度，沿着波传播方向的像素度还要来得大。唯一相等的时候是投影方向跟它的行进方向重合，所以行进方向的像素度是一个最小的像素度。Okay? Now, so that's the reason why in my undergraduate electromagnetics, I'm asking you, I don't know if you have still remember, is the velocity of light, that is 3 times 10 to the 8th, is the highest velocity that we can have? The answer is no. Well, you can easily surpass the speed of light, 3 times 10 to the 3 times 10 to the 8th. 3乘以10的8次方是我们所说的光速，当然它也是电磁波的速度。它是不是最快的速度呢？不是，因为电磁波在任意方向的投影的像素度都会比3乘以10的8次方还要来得高。那上面那句话给你的是一个 extreme example，OK？ So the description on the slides describe an extreme case. That is, here is the propagation direction, here is the equal phase front. If you try to find the velocity, the velocity on the equal phase surface, then it's becomes a number approaching to infinity, because the phase is the same no matter how far have you moving. Okay, so the phase velocity can be greater than actual wave propagation speed. Do you buy it or not? 你们信不信? Okay. Another example is, if you locate it on the seaside, watching the wave coming toward you. So here's the seashore. 岸边了哈。然后这个是波动行进的方向。那波动的速度是多少？假设我们每一条线是等相位的那一个位置啊。那么海浪真正传播的速度会是这里到这一底的距离除上时间嘛，对不对？ So the actual wave propagation speed is the distance between two same wavefront over the time it requires to go from here to here. However, if you are standing on this point, the wavefront move at the same speed from here to move with the same time from here to here, but you have a larger distance. The propagation distance is actually larger than ds. So if you are looking at the projection of the velocity Vp along another direction, you will end up with a speed that is greater than your actual propagating speed. So you can surpass speed of light very easily as long as you are looking at the projection of the phase of light. Can you surpass the speed of light and goes to the past, like what we have seen in the sci-fi movie? No. Why? Because even though that phase velocity can surpass speed of light very easily, if you want to apply information, or if you want to transmit energy along with the wave, then the actual propagation velocity will become smaller. All right? So, yeah, I guess we will stop here. Okay? So then we will discover the so-called group velocity. Phase velocity, group velocity. Phase velocity is always greater than speed of light, while velocity is always smaller than speed of light. Okay, let's take up. I know that it is supposed to be a 20 minutes break. We'll just break for 5 to 10 minutes. Okay? We will resume the lecture 5 to 10 minutes later. 我们先休息一下了哈，但我大概稍微休息一下，我们就继续了。